Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we are going to be discussing the kinetic molecular theory. So if you look at the word kinetic molecular theory, we can break apart the meanings of each part. Kinetic means motion, molecular means with respect to molecules, and a theory is an explanation. So the kinetic molecular theory explains the behaviors of gases, and it does this by examining how gases move at the molecular level. So it's based on the idea that particles of matter are always in motion. Now, real gases have complex interactions, so we use a theoretical ideal gas to simplify these interactions and model real behavior. So the kinetic molecular theory establishes 5 postulates on ideal gas behaviors. So an ideal gas is an imaginary gas that perfectly obeys all aspects of the KMT. So let's investigate each of those postulates. In postulate 1, it states that gases consist of molecules in constant motion. This is consistent with what we already know about the various states of matter. Matter only stops moving at absolute zero, or 0 Kelvin, and this is a temperature that we have never been able to physically achieve. So it makes sense that gases are constantly moving. Postulate 2 states that the molecules of a gas are infinitely small points that are far apart relative to their size. This one is kind of hard to visualize. It works under the assumption that gas molecules are so small that their size is negligible to the size of their entire container. Therefore, the gases occupy no volume. But wait, we know that gases do have volume. When we fill a balloon with air from our lungs, the balloon expands to contain the gas. So how can gases occupy no volume? I want to remind you, these postulates describe ideal gases that simplify real behavior. They do not exist. It's just a simplification. So we can infer that for a real gas, it is mostly empty space. And so real gases have very low density and high compressibility. We're going to talk about those later. The first postulate told us that gas molecules are in constant motion, and the third postulate tells us what happens when the molecules come in contact with something else. So molecules travel in straight lines until they collide with something else, whether that be another gas molecule or the wall of the container. These collisions are elastic, meaning no energy is gained or lost during a collision. The word elastic reminds us of a rubber band. A rubber band can stretch out and it will always return to its original shape. Similarly, gas molecules can run into something else and come away with the same energy that they went into. They don't transfer any energy. Postulate 4 states that there are no attractive or repulsive, so meaning intermolecular forces, between the molecules. This goes back to postulate 3, where we know that gas molecules travel in straight lines unless there is a collision. So the picture here shows how gases might pull on each other, causing molecules to change direction without direct contact. These pulling interactions don't occur in an ideal gas, and molecules only influence each other through collisions. Now our final postulate says that average kinetic energy, so Ke, of the gas particles is directly proportional to the Kelvin temperature of the gas. Now, average kinetic energy is the average energy of motion across all molecules in the gas, or simply how fast the molecules are moving. Therefore, as temperature increases, average kinetic energy increases by the same amount. This means that temperature is a measure of kinetic energy, and this applies to the temperature of any substance, whether solid, liquid, or gas. All temperature is a measure of kinetic energy, or how fast those molecules are moving. Now, if temperature is a measure of kinetic energy, this means that all gases at the same temperature must have the same average kinetic energy. We can graph what the kinetic energy of a sample of a gas looks like at different temperatures in what we call a Maxwell-Boltzmann distribution. Now, this is a little outside of the scope of the course, but it's worth investigating to come to a simple conclusion. In physics, you learn the formula to calculate average kinetic energy. Now, we're not really worried about calculating it, but I want to look at the two variables inside it. In this formula, you're multiplying mass by the velocity squared. Now, velocity is just speed. So what this means is if you have a lower mass, you have to have a higher velocity in order to calculate the same kinetic energy. So, if all gas molecules at the same temperature have the same average kinetic energy, this means that small particles must move faster than large molecules to get the same value. So now that we've gone through the 5 postulates of the KMT, we can summarize the characteristics of an ideal gas. An ideal gas is assumed to have zero volume, they're in constant straight line motion, experience elastic collisions, meaning no energy is lost or gained, have no attractive or repulsive forces toward each other, have an average kinetic energy proportional to temperature, and most importantly, they do not truly exist. So then you're probably asking yourselves what a real gas is. So in a real gas, the particles themselves take up space and therefore have volume. They are still in constant motion, but their collisions are not elastic, meaning that some of that energy will be transferred between molecules or to the walls of the container. The particles do have intermolecular forces, and the average kinetic energy is still proportional to the temperature. So the main differences here is that we do have volume, our collisions are not elastic, and our particles do have intermolecular forces. Basically, those molecules are interacting with each other. So then why use ideal gases if they are nothing like reality? So ideal gases simplify the model we use to describe gas behavior. It takes out variables. Although ideal gases do not exist, real gases can approach ideal gas behavior under certain conditions, specifically when they are moving very quickly and are very spread apart. These conditions minimize the effects of those intermolecular forces and they minimize the number of collisions while increasing the proportion of empty space. We're going to be very spread apart. We're not likely to run into each other. When we do run into each other, it's very fast because we're moving fast. So those intermolecular forces become less important. So we're making it more and more ideal. So this means that gases behave most ideal at high volume and low pressure as well as high temperature. So ideal gases simplify our models. Later in this unit, we're going to talk about gas laws and mathematical representations of gases. We're going to look at it, we're going to treat our gases as if they are ideal, because the reality of what chemists have to account for in lab is much, much more complicated. So you get a bunch of correction factors for things like volume. You get correction factors for things like intermolecular forces, and it gets very complicated very quickly. So ideal gases simplify our math, simplify our models, and let us look at the very basics of what's going on before we start accounting for other things. So that concludes our lesson on kinetic molecular theory.